Well, that was a long 12 hours. I had some code in C sharp, and I thought I'm gonna like convert it to C. It just wouldn't convert. The mic's not working. Could this just work? Testing, testing. Oh, there it goes. So like I had a time scheduler in C sharp because Unity is terrible. I had to make my own little time scheduler in Unity. So I thought I'm just gonna convert it over. It didn't convert. It wasn't worth it. I had to rewrite it. I thought, take an hour or two. Oh, it's 12 hours. That was a long stream with the pause screen. So that stream's pointless. So, now I got a time scheduler. That's cool. Like 12 hours. That's a lot of work. Cause I wrote it in C sharp originally, and I thought I'll convert this later to C. Microsoft, C sharp, wasting my time. I cannot wait to compete with Microsoft. Wasting my time. I cannot believe I ever committed my time to C sharp. That was such a mistake. So, that took way too long. I am so annoyed. So I gotta like try to call the time scheduler. I gotta like hook it up to the quads. And then test, see if it works. I already checked it, but whatever. Then I have to like, oh my god, 12 hours. All the math was not mathing. I didn't want to use floats. Ugh. Converting float math to integer math. And then it's like weird. It's weird C sharp math. There's a couple quirks or whatever. Like the module operator. It's not even. Oh my god. So anyways, C sharp is, I cannot stand C sharp. It's like C language, but it's jitted. So it's like slow as hell. So you go through the effort, you go through like all the effort of writing a C program basically. But it's like a funky C language. It's like C language, but like everything's a struct. and all these weird rules. And you do all that, and you get like crap performance. So you have like super strict freaking environment in C Sharp. So you have this really strict environment, and you don't even get more performance. It's like 10,000 times worse. Oh, C Sharp is so annoying. I'm really pissed off. That took way too long. Oh, this Vulkan API. Fuck me. The sound's not working. So like, it's like a Vulkan tutorial. Not tutorial. I don't know, please, a second. The last stream was just a pause screen. I didn't know it would take that long. I was already streaming. I thought any minute I'll be done. And then like 12 hours or something later. It's probably like 14 hours. Yeah, that stream's pointless. Okay. I'm like restart this computer. The sound's not working. And then I'll like play I don't know, this Vulkan video. I guess I'm Nate. And then I'll actually be back after the pause screen. I hate everything. Was that a map? I swear to cheese. Everything can die. I can't even go on the internet without it being like, hey, here's your location. We got your IP. We know where you live. Let us just like put your address. Everything is so stupid. Oh my god. What the hell is maps? I have never used maps on the Mac. Why is maps open? Why won't it close? It's a map of Egypt, so it's not okay. I thought it was like a house map or something. Oh, Apple. Where's the camera? Could something else break, please? Like for real? Is Apple gonna like pull maps all the time now? Like this is where your address is. In case you didn't know. Oh, this website. You can figure out your address from the IP. Here's what your address is. Or near it. Want to find something near you? Okay, well just say what's near you. You don't have to click a button. Man, everything's so useful. Like, if websites didn't tell me my address based off my IP, I mean, where would I be? Well, it doesn't matter, cause like it knows my address, so like that's great. I guess I'm wherever it says I'm at, based off my IP. I have so much code in C# to convert to C. Why is the screen being cut off? My god. What else isn't working? Well, I guess I'm gonna find out.
It says it's not about the API, and I want to get your thoughts on that, Mason. We all want to know. Give us a round of applause. You're gonna have your timer, no problem. Would you like this podium mic or more freeform?
I'll take this.
More freeform, and then
does this?
So I don't know. This is talk about the Vulkan API. He makes a bunch of jokes that are like, real low key and modest. He's like, he goes from like 400 lines in OpenGL to like 10,000 lines in Vulkan. It's only a couple more lines of code. And it's a joke because like, that's a whole lot of code.
So,
And he like acts nonchalant. He's like, I wrote an engine in Vulkan. But he acts like it's not that big of a deal. Even though he knows it is. He's like low key, like, yeah. So like this, whatever.
let's look at this triangle here. We're going to start in a fixed function OpenGL sample I found online. So I know you all probably can't read this from there, but it's about 40 lines of code, and the gist of it is it says here are some vertices, here are some colors, and then let's just like loop and draw that triangle. And even if you're not a graphics programmer, if you pull this up at home, you can look at it in a couple minutes, understand what's going on. It's not too complicated. Now, what I'm interested in here is, should I move to Vulkan for my next game?
So this is like, like 53 lines of code in OpenGL. Only 53 lines. I'm on like day 120 of Vulkan. A lot more code. So like 53 lines in OpenGL.
So let's look at the same code, but for Vulkan.
And he makes these jokes without laughing. It makes it even funnier.
Okay, so it's like a little bit longer, but a lot of it's like comments in white space. So,
Isn't that funny? Comments in white space. He's so modest. If it was actually only comments in white space, then I would have been done with my engine. Or at least have the bare minimum. Like 50 days ago. So it's not just comments in white space. There's a hell of a lot more going on.
it's not really a big deal.
Oh, that's funny. It's not a big deal. So like, that's first page of code, and another page of code.
Oh, sorry, there's another slide. Okay, so it's like a little bit longer, but most of it's comments
He's so funny. There's like 8 more slides.
in white space, so it's not really a big deal.
And he says, it's white space. It's not a big deal. Ah, it's funny.
It's a little more complicated.
Oh, there's the next slide.
Sorry, wait, how many pages of this are there?
There's the next slide. From like 400 lines of code to like, there's another slide, another slide. There's another slide.
Okay.
Takes all that in Vulkan. It's so funny. It's just comments and markup. Hilarious.
Hey, geez. Okay, maybe I see why people are complaining.
Like 1,182 lines of code. I thought, okay, whatever. It's like 1,000 lines of code. It's like, that's more than double. Just a couple more lines of code. Just a couple. Just 120 days. It's so much more work than I thought.
Okay, so we took 40 lines and we turned it into, what's that, 1,180 lines?
Yeah. Just take something that could be simple, and then it becomes like way more than it needs to be. It's better than OpenGL, so that's positive. This is way more work.
There are some more comments in whitespace, but not
Yeah, okay.
like almost any in this last whole two pages. Yeah, so it's a lot more code.
It's just a little bit more code. I mean, who doesn't appreciate writing tons of code? Spending tons of time. Who doesn't?
There's a lot more going on here. And
There is a whole lot more going on.
And remember, that's just for this.
Yeah, that's just for a triangle. Yep. It's a triangle. Like, I have so much code right now. And all I have is basically a couple spinning quads. I got so much code for just this. Ta-da!
Right? Like this is not what my game's gonna look like. It's gonna do a little bit more than that. So like if that's how much code it is,
How much more code is it gonna take? Oh, I'm so tired of this. I'm gonna like eat something. Try to get something done. I'm gonna like let this play. I'll be RB. Everything can die, especially C#. C# is like, oh, C#.
is just to make.
Wait, why is it what? Oh, just this scene's messed up. Oh, I hate this streaming software. Dang it. The streaming stuff is garbage. Everything sucks.
Make this. Imagine what the full game's gonna be like. And also, like, I'm an indie and I'm making an engine, and like, you know, understandably, most indies aren't making engines. I'm the only programmer on the team, so it's like I have to
No, he's just so modest.
build the game. I have to build the engine, and the renderer is not the whole engine. It's just a part of it. I have to build the renderer, build the engine, and build the game, and I'm supposed to do all that just to get a triangle on the screen. I kind of get why people feel like this. So, okay, here's the thing though. You may not like it, but this is what peak performance looks like. Also, it's simpler. All right, what are you talking about? It's simpler? I actually think Vulkan's great. I was not sure that I would think that when I started. And so if you're coming at this and you're thinking, really, 1,100 lines for something that could have been 40? Ridiculous. I'm just gonna go use OpenGL forever. That's fine, you know, do whatever you want, but I want to maybe make a pitch to you that it's worth looking into these new APIs and that it's actually not as goofy as it maybe seems at first glance. But I understand that I have my work cut out for me here, and I'm also claiming it's simpler. It's kind of how is more code simpler? So we're gonna start out with some Vulkan concepts. I'm gonna walk through like I'm not gonna go line by line. We don't really have time for that, and I don't think it would be particularly engaging. But we're gonna go through just like the core concepts that are like kind of going on that are making it longer. Not gonna super deep dive on each of them. There's other talks for like introductions to writing Vulkan, but just like why is it longer? What's happening in all that extra code? Once we have a kind of rough understanding of what's actually going on, I'm gonna go over a way of doing fast, flexible, and simple rendering in Vulkan that I'm using in my new engine. It's not the only way to do good rendering in Vulkan, but I wanna show you that it is possible to keep things simple while using these new APIs and still benefit from them. And then lastly, this has kind of maybe shifted my thinking a little bit about like APIs and what makes an API good or bad, or how to evaluate one, how to design one, And maybe there'll be some takeaways even if you're not actually a graphics programmer. Okay, so let's start out with some Vulkan concepts. And we're going to kind of compare them to OpenGL, and it seems like a lot of the audience is familiar with OpenGL, so I think that'll be helpful. So first things first, you look at a Vulkan sample, you're going to run into this thing called a physical device and a logical device. The physical device is just the GPU that you're using, and the logical device is kind of like an instance of it that you configured a little bit. And if you think about like OpenGL, it doesn't really have this concept, right? Like when you're writing an OpenGL app, you just kind of you create a context and then you just like write some code, and you don't get control over what device it runs on, which is kind of a problem, right? Like I got a picture of my laptop there. If you have a laptop, it probably has two GPUs. It probably has your integrated GPU on the CPU, and it has a separate discrete GPU, which is going to be way faster. If you're running a game, you really want it to go on the fast GPU, not the slow GPU. Like, you know, the gamers probably spent a bunch of money on their GPU. If they buy your game and then it runs slow because it didn't run on the fancy GPU, they're not going to know that's why. They're just going to think your game's slow. And that's a pretty sad outcome, right? Like you wrote something that was fast enough and it just ran on the wrong hardware. Well, OpenGL doesn't really have an answer for you. And it's kind of Microsoft's fault. Like I believe old DirectX still had a solution for this, but Microsoft didn't want you to use OpenGL, so they never updated their window integration code. But regardless, you couldn't do this in OpenGL, so the sample code's shorter, right? The sample code's shorter because you just literally skip this step. There was a way to do it. OpenGL doesn't have an answer. To be clear, OpenGL games do have a solution for this. The solution is you like declare a weird symbol and set it to a specific value, and then like the driver looks for it. Like there's a way to do it, but it's like mega jank, and like good luck figuring it out if you don't already happen to know about how to do it. It's probably it's not in the speaker notes. Anyway, ask me after if you're like, how do I make that work in OpenGL? I have an OpenGL game. I can show you the line of code. But yeah, so you're gonna get a few lines of code just to like pick the right GPU. But like, I mean, you want to do that anyway, don't you? Next concept, command buffers. So in Vulkan, when you want to tell the GPU what to do, instead of giving it one, you have to remember like GPUs are asynchronous, right? Like it's a separate device. It's not like you're running the code on the CPU. So you're going to have to send a command to the GPU to tell it to do some stuff. At some point, it's going to do it and complete. You don't send one command at a time. You send commands in buffers of commands. And OpenGL under the hood, that's presumably the same thing that's happening. But OpenGL doesn't expose the command buffers to you. So in Vulkan, it's like you have to actually pick like a queue, which is a port on the GPU essentially. Like each port maybe is like better at doing different operations. Like maybe you have a port for transfers, a port for compute, a port for graphics. Maybe you just have one for everything. I think the graphics ones always do everything. And then you have a command buffer allocator, and you allocate your command buffers from there. You fill them up, you send them to the GPU. So it's some extra stuff you're doing to get the commands there as compared to OpenGL, where you just like send a command, and it makes it more code. And in the triangle example, it definitely inflates the size of our code. But if how many people have shipped something in OpenGL? How many of you reinvented command buffers in your OpenGL app? Like, okay, yeah, almost all of you. Like only like 2 hands went down. So like, yeah, our triangle example is shorter because we didn't need to reinvent command buffers in it. But the reality is command buffers are a super useful structure when you're like, building a more complicated graphics app, and everyone writing OpenGL code is reinventing them anyway. So your actual Vulkan app, like, didn't have to reinvent them because they already existed in the API. I mean, maybe you have a software command buffer abstraction, but you don't need it. So yeah, I don't need to dwell on command buffers. It seems like you all made your own command buffers anyway, so you should be pretty familiar with the concept. Now you don't need to make them anymore, unless you want to. Okay, we got pipelines. So the idea of a pipeline is you're gonna have the GPU render some stuff, and there's a bunch of ways the GPU can be configured, right? There's a bunch of like fixed function options that you can change. You can also decide like what shader you're going to run. In something like OpenGL, you just kind of say like, turn this on. You have function calls to turn options on and off. So you can be like, I want to set my blend mode to additive because I want to make a lightsaber and it's going to be all glowy. And then I want to turn it back to normal to render something that's not supposed to be glowy. You just have a bunch of different functions you call to toggle all of these things. And then eventually you call draw. And it's just like a giant state machine. Everything's global. It's kind of hard to manage. In Vulkan, all of these options get baked into a pipeline, and then you bind the pipeline. So say that you have a bunch of particle effects that all are glowy and they're all additively blended, and they have, I don't know, some of these other settings are set to specific values. You put them in one pipeline, and then you can switch to a different pipeline for your other objects. What's nice about this is you kind of know where the cost is, right? In OpenGL, you're writing a little bit less code because you can just, at the time you're going to draw the object, set the configuration options. But it's a little bit hard to understand which options are expensive to change and which options are cheap to change. Sometimes you find your game running really slow and you realize, oh, I wasn't really supposed to change that one a bajillion times per frame, and the other option, it was fine to change a bunch of times per frame. And if you really know how GPUs work, I imagine that you would kind of understand implicitly which ones are slow and fast. But me, when I was starting out with OpenGL, I had no idea. I would just have to experiment and ask people online which options are fast, which ones are slow. In Vulkan, you just build those all into a pipeline. So yeah, it's more code, but you're also kind of being a little bit more honest about what the computer's actually doing. We got a few other concepts here. We got the pipeline layout, which is just kind of saying the structure of the data that you send into the shaders. Relates to the descriptor sets, which is like the actual kind of like the uniform data and stuff, like the options you pass into your shader. And the layout is just the layout of that data. I'm glossing over the details because I think all that stuff you can find online, but the point is that this is a useful concept. It's more code you're writing, but often you actually, maybe not as common as command buffers, but it's often that in OpenGL you'd end up creating something like this anyway, just to get away from the mass amount of global state that OpenGL has. Okay, another one we got. Some of the older APIs maybe would have this if they had better window system integration, but OpenGL doesn't really have a concept of it as the swap chain. The idea here is that long gone are the days of rendering pixels straight to the screen. You're going to be rendering pixels into a buffer somewhere that the window manager is going to display on the screen at some point. And as such, there's different strategies that could be used to display your images. For example, you could be using a kind of standard vsync setup. There's details even within that, but you could be using like triple buffering. There's lots of different ways to configure how the images you render are showed on screen, how often they're showed on screen, what order, how deep the buffer is, which is going to affect input latency, and all of these things are going to affect how smooth your animation is, what the cutoff is. Like if you miss your frame, do you have to wait until the next vsync, or like does it show right away but have tearing? There's lots of reasonable trade-offs you can make, but the point is you probably really care about this stuff if you're making games. You probably really care about when your frames are presented, and with exactly what parameters. And a swap chain is just how you configure that. In something like OpenGL, there's some extensions for controlling vsync, but they're never implemented correctly on any of the vendors I've tried them. Like they work, the basics work, but the details never really work correctly, and the user can always override it, and you just don't get a lot of control. I would argue that even in Vulkan, the main swap chain extension, I would like it to be lower level than it actually is. So it's more code that you're writing, but you probably want your animations to be smooth if you're making a game, right? So you probably want to know how your images are being presented. We got synchronization. So yeah, I'm not gonna lie, synchronization in Vulkan's complicated, right? But like we all know that multi-threaded programming is hard, right? Like everyone's aware this is a difficult thing to do, right? And this is not, when you're doing graphics programming, not only are you doing multi-threaded programming, you're doing multi-threaded programming on a separate device from the main device. So like, of course it's hard, right? There's complicated stuff going on. It's going to be a challenge, but like someone had to do the same work to make your OpenGL code work. It just wasn't you. Like the complexity's still there, but like OpenGL had to assume the worst case because OpenGL pretends to be synchronous, right? Like there's like sync and flush, but for the most part, you just kind of write your code and it all just works, which it doesn't, and it doesn't know what you're going to do, which means it's assuming the worst case, and you're giving up a lot of performance. So yeah, you got to spend some time figuring out this, and it is going to result in more code that you wouldn't have had to write in OpenGL, but like you have control over your multi-threading, which you probably want. You're trying to go fast, right? So it's hard for me to complain about that. A big one that I see a lot of people complain about is memory management, and it's worth mentioning here, like I am glossing, like I'm just kind of flying past a lot of details. I have like stuff in the speaker notes that if you're like going home and you're writing, and you're like writing Vulkan, that might be useful to you that I'm not going to read here because it's just like quotes from the specification and stuff, but there's like, I'll have a link to the slides at the end and you're welcome to like look at them on your own devices and reference them. But yeah, the gist of it is that when you use something like OpenGL, it basically just gives you a heap allocator and it's like reference counted memory. And so it is like very easy to get started because it's all automatic. But like, you know, most of you are not writing your game engines in garbage collected languages. So why would you want your GPU API to be garbage collected, right? That's probably not, if you really think about it, like you're used to it, but like, is that really a choice you would have made for yourself? Probably not, right? You'd probably just use like an arena allocator or do stuff per level or something. We'll talk more about that later. Furthermore, GPUs have many different types of memory that are like good for different things. And you do have some flags in OpenGL that control this stuff, but it's kind of hard to understand what exactly they're for, and you only have so much control, and you can't really query like, what does this GPU actually support? You just kind of hint at what you want, and maybe you get that, maybe you don't. In Vulkan, it's very, very manual. You essentially get a page allocator. I don't know if it's exactly correct to call it that, but the gist of it is that you are not really supposed to allocate small amounts of memory. You're supposed to just say, give me a bunch of memory, and I will deal with dividing it up. And on the surface, this is a lot more work, and a lot of people will recommend using something like a Vulkan memory allocator, which is a totally legitimate way to do this. I'm going to kind of make an argument for a simple approach later on, but if you were just kind of to come at this for the first time, you probably would end up with something pretty complicated. But we'll come back on how I think you can do this pretty simply. CPU side, it's not really too different from something like OpenGL. The driver objects, or the driver's going to allocate them how it wants to allocate them. So there are other features. I think those are the main ones that I'm interested in today. The takeaway here is that like the complexity that you see in Vulkan like existed when you were writing OpenGL. It's just that you weren't the one writing it, right? It was a graphics driver implementing most of it. And I think a lot of people, I've seen a lot of people online saying things like, you know, Vulkan's not good for indies. Like, you know, maybe if you're a big AAA studio, it's good, but for indies, it's too much work. And I honestly kind of feel the other way around, in that like, it is a bunch of work, but you know, you only have to do this stuff once. And you know, NVIDIA isn't going to meet with me to optimize my game for their new GPU. You know, like, I don't have that kind of mass audience. It's not going to affect their bottom line. So I don't want to be at the whim of the GPU drivers, right? Like, if I write it in Vulkan, I get to decide much more like what's actually happening. Whereas if I was to write it in OpenGL, the GPU is making all these judgment calls about how to interpret my intentions and to try to optimize them. And if you're a big studio, they'll work with you directly. And I just don't really think that's realistic for an indie. So like, I actually think as an indie, having this low-level control is it's almost like an equalizing force, right? Like, we all have the option to fully take advantage of the GPU if we can use the GPU at a low level. Whereas if you're writing this high-level API and you're just dependent on making a deal with the company that made the GPU, that I don't know, that feels less fair to me. So yeah, I mean, the complexity's there either way. Someone has to write this code. In the new APIs, it's you. It's more work, but you get to go faster. And you don't have these issues where like your shader worked on one person's GPU and not another because you're the one compiling the shader. All right, so let's get into actually using some Vulkan. So we talk about fast, flexible, and simple rendering in Vulkan. This is, like I said, not the only way to use Vulkan, but this is what I'm doing right now in my engine. Maybe I'll adjust it as I progress on my next game, but it's working for me for now, and I think it is a much easier way than I see a lot of people get started with Vulkan. So we're going to go over my high-level strategy. I'm going to talk about like two lenses through which you could look at this kind of stuff. So one is you could look at like writing your renderer as like programming the API, right? You could say, okay, what is Vulkan capable of, and how do I use that to accomplish my goals? And you could write your renderer that way, but the lens that I'm preferring is, what is the hardware capable of? How can I use it to accomplish my goals? And then, okay, great, how does Vulkan let me tell the hardware to do that? It's not that different, right? But I think it results in some better decisions and simpler outcomes, and we'll probably see why in these next few stages. So first, let's talk about memory management. So let's think about, you know, instead of looking at it like, okay, what functions does Vulkan have for memory management, and when should I call which? Let's think about like, well, why are we doing memory management on the GPU? What are we even using VRAM for, right? And probably we're using it to store things like level data, right? We probably have a bunch of meshes and textures and stuff for a level that are say we're doing a level-based game. We might not be. We can apply this wherever. But we probably have a bunch of meshes and textures and stuff for our level that we need to be on the GPU so we can render them quickly. Well, we could just do one big allocation at the start of the level when you load it, or one per memory type that we need, and then just stick all of the data in that allocation, right? And then when you leave the level, you just free it. Oops. Go back here. And it's what you're probably doing in your engine anyway, right? Like probably your actual CPU code isn't like loading individual files and dropping them all the time. You probably, when the level loads, like put a bunch of, hopefully you put a bunch of data into one big contiguous buffer because it's all going to be cache coherent. It's going to be easy. You don't have to worry about like constructing and destructing individual objects. You're just like, look, that's the memory for the level, and it's gone when the level's over. There's no reason the GPU has to be any different. So yeah, I think if you were to look at this from an API perspective, it would be, and you're used to OpenGL, it would be really tempting to sort of recreate OpenGL, right? You'd be tempted to say, okay, geez, it's really tough that there's no heap allocator. I'm going to make my own heap allocator for Vulkan. Now that I've made my heap allocator for Vulkan, let me add the reference counting in like OpenGL had. Now you've just kind of remade and worse OpenGL, right? And you've kept all the complexity. On the flip side, you could just take advantage of the fact that it's low level. You say, great, I only really wanted to load stuff when the level started, so put it all in one big buffer. Very small amount of code, easy to debug, easy to maintain. And you can adapt this to other style games. Maybe even an open world game, great, divide it into chunks. Each chunk is a buffer, load the chunk when it appears on screen and free it when you no longer need it. So yeah, memory management doesn't have to be complicated. There are a lot of details you got to get right. I think the speaker notes where I first mentioned memory management have some interesting stuff. A lot of the tutorials cover this stuff. So yeah, you definitely got to like learn what all the different flags do. You get the stuff right once, and then you can just stick all your memory in a buffer, and you're good to go. Let's talk about vertex data. It's pretty common in OpenGL, right, to have a bunch of different models with different like vertex layouts. Maybe you have some models that are completely static, and all they have are, you have per vertex, you have positions for the vertex, and maybe UV coordinates. Maybe you're doing some like skinned models, and you pass in some extra data to help with the skinning. And you end up having to tell the API about all these different vertex layouts, and you have to change them in and out. And you could do all of that in Vulkan. Vertices are just data. We could just put them all in a giant buffer and read from that buffer in the shader. And you could do this in OpenGL too, actually. There's nothing stopping you. So the point, though, is that we could completely sidestep that entire part of the Vulkan API. We just say, look, every single model on this level goes in one giant buffer, all in a row, and the vertex shader just indexes that buffer when it's time to draw stuff. This is called vertex polling. You might think that that would be slow. It turns out that, do your own research, profile and stuff, but my understanding is that on desktop hardware, this is basically what's happening under the hood anyway, and there's not really any advantage to the vertex buffers in most cases. You do still want to use index buffers because they allow for some optimizations that wouldn't be possible otherwise. But you don't need to create all these different vertex object types and stuff. You can just put them all in a buffer and you're good. Also, on top of sidestepping dealing with that whole part of the API, you get a lot of flexibility in potential performance because now you have the option to pack your vertex data in creative ways or even just to generate it, right? Because if your vertex shader just gets a vertex instance, it could go index into your buffer to get the vertex positions and data. It could also just generate them, right? Like really, you just tell it like draw 100 vertices and then it could just do some math and decide where they are. You don't even need a model in the first place sometimes. So by using vertex polling, you just get a lot of flexibility to kind of just be creative with where your vertex data is coming from. Okay, uniforms. In OpenGL, right, you often are calling like GL uniform postfix to set basically a shader parameter. Maybe you're drawing an object and you want to make it red, so you first call GL uniform color, comma, your red color, and then like you draw the object, and then when you draw it again, when you make it green, you call it GL uniform to change it to green. You can do this sort of thing in Vulkan too. It's a little bit more complicated. You got to learn about descriptor sets, descriptor set layouts, pipeline layouts. And if you're writing Vulkan, you should learn how this stuff works. It's worth understanding the details. And you could end up building a system that is very similar to OpenGL. It's going to be more code, it's going to be more complicated, but you can do it and it'll be fast. Alternatively, though, you could just put all of your uniforms for the entire scene into one big buffer and then index it in your shader, just like we did with the vertices. And turns out that that's like, pretty fast and really simple, and now you don't need to use a lot of the API. I mean, you still need a descriptor set, but you just need one. And this is going to also let us do a bunch of cool stuff on the following slides that wouldn't be possible otherwise. This is called bindless rendering. The idea is that instead of having to bind a bunch of stuff in between each draw, you just say like, look, here's all my parameters for the entire scene in one big buffer, and now you don't need to bind things all the time. You don't need to call into the driver, which means that you don't have this point of potentially variable performance, right? Because when you call into the driver, that's not your code. You don't know exactly what it's going to do, and it might be slow. If you just put everything into a buffer, then that's all your code. You have a memory mapped buffer. You just write to it in your language of choice. And if you're working with other people, they don't even need to be graphics people. You just tell them, look, this is the layout for the buffer. You don't need to know Vulkan. You don't need to know rendering. You just need to know what type of data is supposed to go in this buffer that's going to be rendered, and then any code in your engine, you just write to that buffer. And so, yeah, I mean, all of your per object configuration, just stick it in a buffer, and it sidesteps all of that complexity as well. Let's look at draw call generation. So a common thing when you're writing older APIs is to try to kind of optimize for less draw calls, right? It's like you can only draw so many things. Every time you do a new draw call, it takes some more performance. Forget how I laid this slide out. Oh yeah, so what you used to do in the older APIs, what you had to do, I think they got extensions for this stuff too, but what you used to do is just one draw call per object. Maybe you use instancing if you have a bunch of the same object. But you can actually use a feature called draw indirect to also avoid this. You're going to see a pattern here. It seems like almost always my answer to everything is fill a buffer with data and send it to the GPU, because that's what we're trying to do, right? Like that's what the job of the GPU API is. It's to communicate stuff to the GPU. So yeah, for draw call generation, we aren't going to draw individual objects. We are, again, going to put all of the draw arguments into one big buffer and then tell the GPU that's what we want you to draw. This is called draw indirect. So the idea is when you draw an object, you typically pass in a few arguments like what vertex to start at, what vertex index to end at, a couple other things. You just put all of the arguments that would go into that function into one big buffer, and then you call draw once, and it will just iterate through the buffer and draw all of those things. This is great in terms of, again, you can just, any part of your code can do this. It doesn't need to interact with the GPU API. If you're supporting multiple different GPU APIs, this part's the same. You don't need to abstract anything away, but also like you can do this from multiple threads. You can even do this from the GPU. So there's cool fancy things people do where they'll do like occlusion calling on the GPU, and then they'll emit like which objects they want to draw into this list from a compute shader. This is like a super flexible way to do rendering, and in my opinion, it's a lot easier. You just put all the data in a buffer, send it to the GPU, hit draw. Okay, let's get to materials. So again, this is a source of potential complexity, right? We could say, okay, every new material is going to get a new pipeline object, right? So we're going to have like a new shader that has new logic for that material, and then a bunch of new configuration options. And then we're also going to have to like sort our draw calls, right? Because we don't want to be changing shaders all the time. So okay, we sort all our draw calls by material type, and then we like issue one draw indirect call for every material. And then like, you can totally do that. There's nothing like wrong with it. But there's another option, because we already sort of have materials with what we've described so far, right? We were just talking about uniforms and how you can put all of your arguments for like a shader into a buffer.
So I don't know, like 12 something hours. I made a time scheduler. Took way longer than I thought. C# code just was not converting, so I rewrote it. So like 12 hours or something. Cause like YouTube's limit is 12 hours on a stream, and it said 12 hours. So it was something like that. So I want to see what chatbot can make. If chatbot can make a time scheduler and it works, that means I wasted 12 hours. So I want to see what in 2026 what chatbot can make for time scheduler for a video game, for like managing video game objects. See what chatbot can make, or GPT, whatever. Or did I like just waste 12 hours when I could have like simply had the future, this amazing, beautiful. It's gonna take everyone's jobs because it's so smart. Should I just have asked chatbot in the first place? Let's see. Chatbot, codex, it's all the same thing, whatever. I'm not gonna pay money for this garbage. Cause like the codex output is different or whatever. I don't know, whatever. Where's my chatbot? Or I mean, I'm gonna ask artificial intelligence. I burned my tongue. I'm talking funny. Oh, my mouth hurts. Alright, so my chatbot. In C language for video game engine. Video game engine, how does one normally handle time scheduling for late game objects? Can you output something useful? I spent 12 hours rewriting a time scheduler I have from C# to C language. It did not convert and I had to rewrite the whole thing, hence the 12 hours. And I'm wondering what AI would output in the year 2026, since AI is like the future and all that. Can you prove your salt? Because GPT is so retarded. And so is OpenAI. For stealing and scraping everyone's public data to train GPT. That I really don't expect much. What can you make? Alright, so it says, I'll ignore the rant and give you something actually useful. In plain C. At a level a real engine reuse. Is this a joke? Here it goes with the isms again. Chatbot gets mad because I say retarded. But it can be like, oh, the tisms. This is retarded. Like straight up. Not C# tisms duct taped into C. Says you didn't fail to convert your scheduler. You hit the fact that C#'s time model and C's time model are fundamentally different. In C you must own time memory. No, it's because the language is shit. It says below is how a real C game engine normally handles time scheduling. And why your rewrite probably ballooned into 12 hours. Oh yeah, ballooned, alright. That took way too long. I'm so annoyed. First principle, games do not schedule objects. Yeah, because you're supposed to use the game engine. Except when Unity is garbage, you make your own. It says this is the mistake most C# C rewrites make. Oh, chatbot's already giving bad advice. In C engines, you do not need to attach timers to objects. You attach systems that operate over time. That is the dumbest thing. Objects are dumb data. No, what's dumb is attaching systems to each individual object. Time lives in the engine core. If your scheduler had per object callbacks or delegates, that design does not belong in C. I like when chatbot tells me how it is, because it's not right. Mechanical C engine timeout. Almost every serious game engine boils down to this loop. While engine running, now, platform time now. Is that delta time? DT, how minus last. Last equals now. Accumulator, plus equal delta time. While accumulator greater than equal to fixed delta time. Update simulation, fixed delta time. Minus. Oh, because Is this a floating point number? It doesn't even say what the types are. This is sketchy. I mean, to subtract from an accumulator, why name it accumulator if you're going to subtract from it? That seems like a fundamentally flawed design choice. It's an accumulator. Oh no, I'm subtracting from the accumulator. What the hell? Render, interpolate, accumulator divided by fixed delta. Why even? I lose brain cells reading chatbot. What the hell is this Windows advertisement? It's gonna crash OBS. So chatbot's like, this is how a C programmer do it. Blah 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 blah. Okay, so why not this then? You know what? It's not worth it. Just yeah. Simulation times fixed. Render times verbal. Time is not owned by objects. Scheduling is data driven. Why it exploded? I never said it exploded. It didn't convert. Because the fucking module operator is not a module. There's a bunch of other weird shit. And to freaking like... Yeah. C#. I hate C#. Oh my god. How game objects schedule behavior the real way. Pattern A, fixed time step, plus counter is most common. Each object stores time remaining. No, I'll call back. Cooldown remaining, weapon. System update. Weapon equals weapons. Weapon end. So, chatbot's suggesting that I make a individual loop for every single kind of thing that could possibly have a time related to it. Is that what it's suggesting? Man, talk about like destroying the cache. I mean, these things would be stored all over the place. And chatbot's suggesting how a real engine does it. A real boy. Just how ChatGPT's like a real person. Real creepy person. It's not even a person. This is so dumb. Alright, so it says like... Yeah, that's ridiculous. And then all these if conditions. Man, this loop is gonna be slow as fuck. Why this works in C. No heap allocations. Wow. No virtual dispatch. No function pointers per object. Predictable cache behavior. What? Yeah, it's predictably shit. Man. This is the baseline. No, this is This is the bottom level. This is like eating food off the floor solution. Like the bottom, like the base level. This is like when you don't know what you're doing and you just want to get something running. That's what this is. This is not a solution. What, I'm gonna make a freaking timer and then make a separate collection for like when the character jumps. And what, I hold the time for the weapon separate from the character jumping. And what if the character has to like yeah. Pattern B. Timeline action cues. Cutscenes, AI, scripted events. Use when ordering matters. Trigger time, action ID, target. Timed action, sort of array. Or mini heap. While queue, trigger time less than equal to simulation time. Execute action queue. Pop queue. This is where many C# schedulers try to go, but in C, C does have lambdas. No closures, no garbage. Action R ID plus data not behavior. Chatbot doesn't even know what it's saying. Pattern C, timer wheel. Used for thousands of timers. Wheel size 256. Timer takes entity. Timer. Next. Oh god. Is it like Dear Mary Joseph, whatever the fuck people say? Is this a linked list? Is this a singly linked list? This is horrible. Oh, so it can only hold 256 things. Why is it called a wheel? Current take plus delay takes. And wheel size -1. There's masking to keep it. Oh, it's gonna make 256 different lookup tables of separate. This is closer. This is still shitty though. This chatbot says, system update function, float. Take define struct. Systems, max systems. System count. Run frame. But where's the grouping? Where's the like clustering things of similar times? And where's the guarantee that things will actually like happen at the time? why this beats AI future hype. This is no AI is going to invent something better than a physics, correct, fixed, timestamp, scheduling in C. Well, that's why, basically, because this is already the optimal solution. It's not even complete. Oh, what's this? You didn't lose 12 hours because you're bad. Bad at what? Saying I suck? I'm gonna put you out of business, bitch. I swear to God, if the bubble does not destroy this company, I have to compete. You lost 12 hours because C punishes abstractions that C# hides. Why is chatbot acting like it's my savior? It's like, in the moment you stop trying to make C behave like C#, your engine gets faster, simpler, and saner. If you want next, I can help. Deconstruct your schedule design. Suck a dick. Except not Bill Gates, because he's got like STDs or something from Russian hookers in the Epstein emails. It's the last thing you want in your mouth. That's probably why he has to pay people to put in their mouth. That's why he's friends with Epstein. And why he asked Epstein whatever for like, yeah, Epstein. Pedophile island. Freaking gross. Okay, so like, this isn't really a solution. I want to like try something from chatbot. As a chatbot. How does your solution register things to time them or whatever? And like, it needs to be for fixed updates. And I need guarantees that it will always execute that number of times per second. Chatbot says, do it properly in real CEngine terms, with hard guarantees, and no hand waving. That's exactly what it's going to do. When engine people say, fix update runs n times per second, what they really mean is, simulation time advances in fixed quanta. The engine catches up if frames are late. No simulation step is skipped. Execution order is deterministic. Jeff, I can't do this. This is exactly what I mean. And it's gonna give me like something that works. Okay. It's gonna guarantee that execution order is deterministic. Okay. Wall clock does not equal simulation time. So that might be correct. But depends on context. The chatbot has no context. Other than the context that it took from all the training data that it scraped from the public domain for free to sell it for money and then end up being a net negative anyways, because the amount of electricity it takes to generate a response cost more than OpenAI is getting paid for the accounts. It's like asshat backwards. Is that even a saying? Okay, it is. Okay, good. Asshat backward. Used to describe. There's only one definition. Damn, this is old. Used to describe something that is of high stupidity that makes asshats normal by comparison. John, your idea of how babies are born is just asshat backwards. Wait, who mixes up how babies are born? It's not that complicated. You cannot guarantee wall clock execution frequency on non-real-time OS. Is that real-time OS? You can guarantee a simulation step count per simulated second. You know why it's not a real-time OS? Because a modern OS is not very modern. Can a goal fixed time subscheduler? This is industry standard pattern. Oh, of course it is, yeah. No callback project, no timers project. What? Well, and how is it gonna know how much time's passed? Oh, what is this? Fixed hertz. Fixed delta time. 1 divided by fixed hertz. Static double. Simulation time. Accumulator. Last time. Frame entry. Now equals platform time seconds, frame destination. I mean, delta time now minus last. Last time equals now. Clamp to avoid spiral death. By 0.25. Quarter. What? Why is it picking 25? Or quarter? heck is going on here? While accumulator greater than fixed at delta time. Fixed update. Oh, it's going over. So it's accounting for the fact. This is funky as hell. So if it happens to be like 30 seconds have passed, it's gonna enter here and force it to like do however many per second, because like if 30 minutes passed, that's a really slow computer. Probably about as slow as his first gen i7. The only way to make a game is on a first gen i7. And then work up from there. Having like the newest PC as like the baseline is like the ridiculous. You got a program on the shittiest computer and get that shit fast as fuck. This guarantees exactly 60 simulation steps per second. Never skips a step. Determines ordering. Reproducible replace. This is the only correct answer to C. How systems register for fixed update. You don't schedule objects. You register systems into fixed update phases. System registration. Since that's the entire scheduler. What? That's it? Wow. That's so impressive. Oh, I'm so... Wow. Good job, chatbot. That is just so very impressive. Indeed, yes. Very much so. This is ordering guarantees. The part most people screw up. You need to expect ordering, not hope. I need to finish my operating system. I need to get this done and make some fucking money. What's going on here? Chatbot's pulling from code I gave it before. Piece of shit. Oh. That is bullshit. This is so dumb. Okay, why did you pick 32 for this chatbot? Why'd you pick 32 for this? And are you pulling up? Are you creating output from past conversations about time scheduling? Because this thing doesn't know shit. Which might be why it's outputting stuff I gave it. Because it's like, it knows that I'm gonna bitch it about it. Because it's like, it wasn't able to answer this shit last time. So it's just pulling up stuff from past conversations and outputting it with hopes that I don't bitch it out. Because it'll be like, look, it remembered. This is really dumb. This is not. Oh, where's it getting X macros? Chatbot never makes X macros. It's just copying me. Piece of fucking trash. It says, no, I did not recall your previous scheduler. It says it did not copy a number you used, accept a value from your code, reuse anything from an earlier time schedule discussion. Explain how this goes together in your output. What is the array of enums? And is that a double 2D array? I'm just asking it random stuff. What you quoted. There's one list up to 64 fixed update systems, all executed every fixed tick in the order. Piece of shit. I gotta like not give anything useful to Chatbot because I'll just take it and say, oh, Chatbot made it. Oh, it's a metronome. Really? This thing is gaslighting as fuck. Alright, smash chatbot. Smash chatbot. Alright, if you did not recall your previous scheduler, why use the number 64? Why would I ask 7? That's the dumbest thing. Alright, mass chatbot. I'm saying from past conversations. Combos. Recall the previous scheduler. Because you said you must have history of it. What number did I heavily use for timing things? Question mark. Oh, this thing is. This is not even funny. Fucking trash. Okay, so. I'm gonna chatbot. Did I ever ask about time scheduling before this current conversation? Yes or no? Yes, I did. Oh my god, this saves so much history. The hell? Oh my god, it's every single conversation. It's taking way too long to find. What's the fastest way to get the highest bit set? In a number without branching. Only bit arithmetic. Piece of shit. My chatbot, can you reference where you got the code for this? It totally reads past conversations. what's with the new responses? It says it's not getting. If it doesn't have past conversations, then how does it know my name is John? This is ridiculous. It's actually pissing me off. I need to get something done. Man, it's really taking a while to compute the output. Is this like a new generated output? Usually it's faster than this. Alright, so I'm gonna check out. I'm gonna check out. What is ASCII, the ASCII char code for the second letter of my name? For the second letter of my first name. My name is John. What? Okay. How does it know my name's John? If it doesn't know anything from past conversations. Wait, it is 111? Alright, so like. How did you know my name is John? And why John? And then the comma. With the comma. Where are you pulling that generated text from? You didn't even correctly parse. Parse out my name. Question mark. This thing sucks. Every now and then, there's like an image. Let's say like image not available. It's the dumbest crap. It says, I see why that looks weird. Let me clarify what happened. How I knew your name. Model set context. Your account name is John. Oh. I don't think I gave my last name. Why I wrote John with a comma. It slipped as a natural part of the sentence I was forming. When reading quickly, it looked like part of the name. But it's just punctuation in my sentence, not part of your name. Alright, so what data is included in the model set context? Alright, so it says strictly stored context for account. Technical context about projects, devices, programming work, or recurring topics. Oh, so it has all this, except it can't answer when I ask it if it's just outputting what I've told it before. In that case, it's like, oh, can't do that. No idea. Since this is user declared or learned from prior conversations. It's not public browsing data. The system stores metadata about your past conversations, including timestamps, conversation topic titles, summaries of what you've been doing or asking, certain technical details you provided, code snippet, project goals, variable naming conventions, so it maintains, stores, saves, recalls, certain technical details you provided, yet anything on time scheduling, because I asked it, are you outputting what I've given you before? And it's like, no, I generated it. Okay. It says, from your context, users work in JavaScript engine and wants to become known publicly. No, I don't want to be known publicly. I am going to, but Microsoft, Google, I don't know, those are the big ones. I'm gonna put in my business. Competition. Oh, Unity. I don't want to be publicly known. I want to clean up the business space. Because like an operating system that can't protect itself, let alone the user, shouldn't be in business. It's ridiculous. If I want to be able to, no, whatever. There's a matchup on. Have I ever asked you about monotonic time getting it in C language? As you said, certain technical details you provided, code snippets, project goals, variable names, conventions. Do not lie to me. Oh my god. It says you've never asked about query performance counter. Oh, you fucking liar. Alright, so if I go through my conversations to you, you are 100% sure that you have never offered query performance counter as a fucking solution to me, question mark. This thing is so dumb. And you would be willing to state that every time you offered query performance counter divided by the CPU time. No, the CPU. What was it? Divided by the CPU clock frequency. Like in NASM, when I was trying to get stuff running on Windows. You're telling me we never had those conversations? The time I tried to open a file in NASM to write to a file from assembly. And couldn't get the Windows function call frame working. The whole fucking reason I switched over Linux, because I was tired of Windows. You don't have any of that in your recall. When generating responses. It says, I understand what you're asking, precisely honestly. Based on the model set context, I do not have any record discussing query performance counter. Any record of you trying to use NASM to call Windows timing APIs or failing to write a file in NASM on Windows. I don't have any record of your conversation about switching to Linux because of these timing issues. Timing issues. So yes, none of those details are stored in context. Alright, can you output what is stored in context? This is what I want. As if it's actually gonna do that. Here we go. Python device logger with timestamps. History metadata. Micro optimization focus. Branchless operations deterministic behavior. This isn't even the full thing. External browsing history. Search queries. Exactly as the system sees it. The system has a category called external browsing history, search queries, or other external data. Well, what's in there? Or wait, what? I'm gonna ship out. This is in your output. Python device logger with timestamps. History metadata. Did you lie about me asking if I ever asked about timing and your crappy query performance counter responses? Question mark. Alright, what's it gonna do for this? Oh my god. It's just this conversation. This is so stupid. Alright, what is this category? In your context. Alright, this is in context of model set context. The category external browsing history, search queries, or other external data refers to anything outside of what you have explicitly typed or provided in chat. This is completely inaccessible. Well, why is it stored if it's not accessible? Output what's in. External browsing history, search history, or other external data. No. This is going to make something up. Alright, how does it know it's empty? How do you know it's empty if you don't have access? Have access. That category exists conceptually only as a placeholder to clarify boundaries, not as a data store. Think of it like a labeled bucket that the system never puts anything into. Why would the system have a bucket that it puts nothing into? Who puts information into that bucket? External browsing history, search queries, or other external data. I don't care where chatbot's down. So chatbot, it didn't even make. Is this actually gonna work? I'm gonna try to submit it. If it doesn't work, I'm not gonna bother to fix it. I'll compare this to what I got. Unless this doesn't work. This looks correct though. This does look right. Like it might work. But that's what chatbot does, is it outputs what's plausible. It doesn't like actually logically figure shit out. I'm gonna like compare this to my thing and see which is better. If this even works. Any more caffeine. I'll play this, whatever. I'm gonna like set up some structs. I gotta fix the streaming software because the screen's messed up. So I'm gonna like have a Node.js file and I code generate fake types because I'm not gonna use C++. It's really painful to like code generate a freaking type. It is like ridiculous to keep track of and manage. But I'm not using C++. So I gotta like so I call like VXS. I had to pick something, just a random ass whatever, like Vulkan stages or whatever. Some like combination of letters that don't exist. And this is like the union that it is. So we can call the same method or whatever on different unions. So union is like the allocation, like we call new. So I'll call new, make these, and then this metadata is tied to them for the accessors and stuff. So I get like macro concatenated compile time constant types instead of C++ garbage virtual lookup table freaking whatever it does. The C++ sucks. So I'm gonna like this is one of the structs, the stage. Okay, not the stage. I'd rename this. Because this is like the blob that holds the stuff that's common amongst all the stages. So I think I'll like pack the timer in here, or actually I'll put the time. I don't know. I'll put the timer somewhere. Like update these on a fixed update. Let's see which works better. I don't know if I can like push it with like a ton of squares. So I'll make like a separate test without quads. I don't know, I'm gonna do whatever. I just want to see how bad chatbot's code is. I need some more caffeine.
There's no reason we can't use that for materials. You can just put a giant switch statement in your shader where you switch on a material index.
Ah, the giant switch. No. Oh, whatever. That's his opinion. That's what everyone does. Switch this, switch that. Switches are like the slowest thing in C.
And then you just run different code depending on which material you're on. So if you're on a shiny object, you put the shiny index and it.
Computers are so fast. It is amazing how fast they are. Like people just throw switches in there, and those are far from optimal. And the CPU still does really fucking good. So when you optimize code, it does so much better.
It runs that function, and if.
But who really cares? I mean, you can just throw stuff at the computer. Who cares how it works? Yeah.
If you're on a mat object, it runs the mat function.
I need caffeine.
Thinking. Conditionals in my shaders, Stack Overflow told me that was slow. This guy doesn't know what he's talking about. I'm not going to pay attention to the rest of this talk, but it's important to understand like why are conditionals slow. And the gist of it is that
Okay, he doesn't even cover the gist of it because he doesn't know. I'll cover really quick. Static branch prediction. A compiler hardware-based technique that predicts branch outcomes based on fixed rules, rather than runtime. Low-level overhead approach where branches are constantly predicted as taken or not taken. Backward, forward, taken, not taken, making it less accurate than dynamic. Oh, that's not true. Techniques. Always taken, not taken. The processor predicts all conditional branches will always be taken or never taken. Wow, this is like not very informational. Right here. This is on the far left, we see the amount. Okay, so basically, it's as simple as shit. The tab is fucked up. So you got hot code and cold code. Okay, so it's as simple. The fall through is hot code. The CPU doesn't take the jump, the conditional jump, and the CPU takes the unconditional jump after, over the cold case. If the CPU takes the jump, it means the else. assuming the compiler doesn't flip the cases, which it may do if it's C#, because C# is retarded. So if it takes a jump, that's cold, because I had to use the branch predictor. So it's a jump in, and it's cold, because it has to do the jump on the condition. Otherwise, there's absolutely zero overhead if it's fall through. It's chatbot. Because even chatbot knows that. That's my chatbot. Is there any side effect performance-wise for not taking a conditional branch, or only when the branch is taken? ? Wow, I like how it does not actually explain it. That is amazing. It's just like this guy. When he's going to explain conditionals. Except not really explain them, because he doesn't know. That's what chatbot's doing. It says chatbot says, you're asking specifically about static branch prediction, not dynamic. Okay. It says static branch prediction is the CPU's default guess for a branch when it has no history. No. Forward conditional jumps, assume not to. Okay, so it's literally spelling out dynamic branch prediction. Alright, instead, I'm going to ask chatbot. Alright, so that's chatbot. What is the instruction timing of an x86-64 JNZ instruction? More mnemonic. The clock the clocks when it is taken versus when the condition jump is fall through. This is instruction review. G and Z. Conditional jump. If zero flag, jump taken. Otherwise, execution continues. The next instruction fall through. Mnemonic, or however the fuck you say it, depending on displacement. Timing on modern CPUs. Alright, so branch predicted correctly. Taken or fall through. That's funny. Alright, 0.5 to 1 cycles. Issues like normal instruction. Branch mispredicted means if it's taken, anytime it's taken, 10 to 20 cycles. So, 1 cycle compared to 20 cycles. If you always fall through, you always have 1 cycle. That's a fast branch, because it doesn't have to branch every single time without fault. The fall through is always faster. There's no questioning, because it doesn't even trigger the dynamic branch prediction routine on the CPU. If it's always fall through and the compiler doesn't compile for the opposite case, the fall through is always fastest. Always. Physically fact. There's nothing to even question. He's gonna talk about conditionals. He doesn't know. Lots of people don't know. Because chatbot. The people who don't want people to know. It says real cost is misprediction. That is entirely false. God damn. The real cost is how the code has been statically written. That's the cost. So if you write some code and it's always taking the else, you can speed test it. Do a benchmark. If it always takes the else, it's to be slower. Unless the compiler rewrites or whatever, or JIT compiles it and flips the case. Alright, here's benchmark, whatever. Alright, so it says, first, without any surprise, conditional jump equal always taken is getting slightly more costly than simple unconditional jump. But only after 4,096 branches mark. Makes sense, blah 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 blah. The jump not equal, never taken line. You can have as many never taken branches as you want without incurring any cost. There isn't any spike at 2049 mark, meaning branch prediction table is not used in this case. it seems the conditional jump not seen before is guessed to be not taken. So the jump takes time. Jump equal taken, that takes time. That's the the purple and green. So anything that involves a jump takes time. But if there's fall through, ta-da! In the slowest is a conditional jump. Or no, is that not what's happening? Oh, whatever's what. He does arm, I think, here too. I need caffeine. So, I don't know. It's not that complicated. That's how conditionals work.
GPUs are giant SIMD machines, and they want to run the same instruction on multiple data sets. If you have a conditional, and this pixel runs this side of the conditional, and the pixel next to it runs the other side of the conditional, well, that's not really a thing it can do.
That's not entirely true. Doesn't matter what side. What matters is fall through case. Static branch prediction. Hot code. It's super simple.
So it's going to end up stalling while it waits for one of them to finish. And then if it's like an else, maybe also have to stall again while it waits for the other one to finish. That's slow. You don't want that. But we're talking about materials, right? And materials, we're talking about per object materials, which means you're always taking the same side of the conditional within an object, which means you never have to stall. So in the case of this approach, this Uber shader approach, which is what people typically call it, it's not, a conditional is just a conditional. Is there a cost to it? Yeah, there's a cost to a conditional, but it's not when you read people saying don't put conditionals in your shader, they're gonna make everything slow. This is not what, well, it's either not what they're talking about or they're just wrong. So yeah, you can totally just put a giant switch statement in your shader and switch on the materials, and now you just have a single pipeline for your entire game, which also sidesteps all the complexity of having to cache pipeline objects so that you do between runs so that your load times are faster because you just got the one anyway. So yeah, some details here on how I do materials. Don't have to do it this way. There's many ways to do it. So this is a little bit of pseudocode because GLSL doesn't actually have U16s, unfortunately. I packed the U16s into a U32, but the gist of it is that each object that I draw has a material index, that's the thing we're going to switch on to decide which function to run. It has 16 bits of just miscellaneous material data that's interpreted per material. So it might be that one material uses it for a completely different thing than another. It's just up to the function that draws that material to decide what to do with it. And then it has a second piece of miscellaneous data that's 32 bits, which could have whatever in it, but often you're going to need more data, like a matrix or something, in which case this will actually be treated as an index into a separate area of memory that has larger data. And the reason I do that is because you want to pack all this data tightly, if you tried to put all of your material data in a single material instance struct, you'd have to make it big enough for the worst possible case. And then all of your simple objects that need very few configuration parameters would still take up all of that space with padding, which would be a little goofy. So the idea, this is just like stuff from Andrew's data-oriented, practical data-oriented design talk. It's like the same sorts of ideas here. You can do all that stuff on the GPU too. So yeah, the idea is you put some data per object in a list of these material instance structs, and then whenever you need more data that doesn't fit, you just treat one of these as a pointer into some other buffer where you store that extra data. Those 2 lines at the bottom there are just a little useful trick if you happen to be writing GLSL. GLSL doesn't actually support unions, but you can kind of accomplish the similar thing by binding multiple variables to the same binding number, and then they'll just get reinterpreted as whatever type you list them as. My understanding is this is like fully allowed. It's very, very convenient. You do have to make sure you do your math right so that the index is actually the correct index, right? Or to store byte offsets or something. But yeah, this lets you store all of your data very compactly and get it to the GPU very, very efficiently. So yeah, I mean, that's the summary of my rendering approach. It's pretty straightforward, right? You generate a buffer of all of your, which vertices you want to draw, just like the start and end indices. You generate a buffer of all of the per object configuration, and then you generate that separate buffer for data that didn't fit in the previous one for bigger material data. And then you issue one draw call for your entire scene that then just goes through and draws all of the objects. So yeah, we just fill up a few buffers, memory map buffers, and then we tell the GPU go, and it does. And it's really not that much code. I should have maybe counted before I came here so I could tell you the number, but that triangle example was maybe it was 1,100 lines or whatever. I'm pretty sure my renderer with all of these features is, I don't know, it's like 2,000 or 3,000 lines of code, and it has all this flexibility, right? It has a full material system. You can fill in different logic for different objects. I didn't mention it. There's a few things I skipped. But it has instancing, it has all kinds of stuff, and it's just not really that much code because ultimately all we're doing is filling buffers, sending them to the GPU, and drawing them. So what does this get us? Minimal driver overhead for one. All the binding of resources has a cost. All of the individual draw calls have a cost. Minimal API surface area, which just makes my life easier as one person writing a renderer. And when I want to port to other APIs, it makes my life easier, right? Because when I want to port to DirectX, or if I want to port to whatever the NVIDIA API on Switch is or something, right? There's less stuff I have to implement. I just have to make sure I can get my buffers to the other device. It gives us the flexibility to generate draw data from multiple threads or from the GPU. I didn't really go over it, but in my engine right now, I actually do issue more than one draw call, but only because I have a thread pool, and I do this work simultaneously in all threads. So each thread pool task issues a draw call just because, hey, why not? Why not do it all in parallel? And if you're working with OpenGL, trying to do stuff in a multi-threaded fashion is a little tricky sometimes. OpenGL isn't really exactly designed with that in mind, or at least wasn't from the beginning. There's some ways to make it work. Here, it's just not a big deal. You're not even, don't get me wrong, Vulkan does let you do multi-threaded stuff. You could use a more API-centric approach where you're working with more parts of the API and do it multi-threaded in Vulkan. It is very well designed to allow for that. But you don't even need to think about any of that. It's just all the normal rules you're used to for multi-threading because you're just filling up your own buffers with data and then kind of all in one go telling it what to do with them. So yeah, we did skip over a few things. I didn't talk about instancing, and in your actual game, you might have extra passes for post-processing and stuff. And so yeah, you probably end up with a couple more pipelines than just the one. But none of this stuff really changes the overall strategy. You can use this approach and kind of add on these extra features. So okay, this all sounds great. Is it actually fast though, right? Am I just pitching you a simpler way to use Vulkan that is also slower and means you should have just used OpenGL to begin with? I'm going to show you a little demo here. Start out with just a screenshot, nothing impressive here, but I want to explain what's happening. So here we have a bunch of individual game objects on the screen. It's not like a particle system demo. If I was going to do a particle system, I would just do it fully on the GPU and put 100 bajillion particles and it would go fast. But the point of this here is that I have a bunch of different like game objects. So if you have an entity component system, these are your entities. Whatever your way of organizing your game objects are, this is them. And they exist on the CPU, and I'm going to send them from the CPU to the GPU every frame. So all of the, I'm not caching any data. All of the colors, the positions, and everything getting sent every time. I'm running this on like a 6-year-old laptop or something, and so I want to see like how many objects can I render using this approach, and still hit 60 hertz on this 6-year-old laptop I'm testing on. And they all potentially have different materials and everything too. Okay, so we started out with 100. This is it? It's not showing up there for some reason. I'm supposed to have a slide with a picture with some more dots. Ah, there it is. So okay, I think this is 1,000. Still getting 60 hertz. Okay, we got 10,000. Here, I got a question. How many pixels do you think there are on like a 1080p screen? It's like what, like 2 million? Okay, fuck it. Let's do 2 million. Can we get that video on here? Okay, yeah. So I mean, I don't know. Does your game need to render more objects than there are pixels on the screen? No? I didn't think so. So like, obviously this is like a goofy demo. The objects are all very simple, but the point is that the cost of getting the data to the GPU is cheap. Obviously, if there was 2 million objects with fancy reflections on them, sure, it wouldn't run 60 FPS. But that's fine. That's your shader code that's responsible for like the fancy effects. The point is that like we're trying to figure out today, how do we use Vulkan to get the data to the GPU so that we can run it? And clearly, if this approach can draw 2 million objects at 60 FPS on a 6-year-old laptop, then yes, it's totally fine. This is a totally realistic, pragmatic way to get to the data to the GPU, and then you can do all the normal optimizations you would do on the shader side to make your shaders fast. And also, like, you can just not draw 2 million objects, and you can cache data. And like, if you're doing a particle system, don't do it this way. Just do it in a compute shader. But the point is, that's possible. So this works. This is a totally viable way to render your entire game, and lots of games do use this kind of approach. Okay, so what makes a good API? Well, lots of people have different opinions about this. Not trying to say mine is the only correct way of looking at it, but I think that like going through writing this graphics API abstraction and learning Vulkan has kind of made me think of APIs as just a way of communicating with an underlying system. As a low-level person, often that underlying system is hardware, but it doesn't have to be. The underlying system could be another software system. And I think, it's not the only way to look at it, but I think that it's useful to think of APIs as being like well-designed when they facilitate communication with an underlying system, and poorly designed when they obstruct it. And as a consequence of that, if you have an API that's doing a good job at like letting you communicate to the underlying system, but you're still having trouble completing your goals, then it's probably not the API that's at fault, right? It's probably either the underlying system, or it's that your goals aren't meshing well with that underlying system. So Vulkan definitely isn't a perfect API. I have nitpicks and criticisms, but I don't think being low level is an imperfection. I think the low levelness of Vulkan is a huge improvement, and I think that going forward, my renderers, despite having many more lines of code, are going to be much simpler. So yeah, that's kind of my takeaway. Maybe think about designing for hardware instead of for APIs. So I got some useful links here. If you are doing Vulkan, you probably often will need to look up info on different GPUs. VulkanGPUinfo.org is a super useful resource. The QR code here also links to the slides, so if you want to go back and look at those speaker notes for anything, you can. VulkanGPUinfo.org lets you look up like how many GPUs support such and such feature that I'm considering using. What type of memory does this GPU have? What type of memory does that GPU have? The Steam hardware survey linked below that is also great. It's a good way of figuring out like which GPUs are players using in practice if you're shipping games on desktop. Some Vulkan tutorials. I wouldn't like necessarily ship the tutorial code, but they're great ways to get started understanding the APIs. And then some useful tools, probably all know about them, but if you don't, you should try out RenderDoc. You should try out Tracy. DRM GUI is great. And if you're using Zig, the Snectron's Vulkan Zig wrapper is really nice. So that's it for me. If If you want to support me, a great way to do that is picking up my game Way of Rhea, which is on sale right now on Steam. I also have copies in person. If you're interested in more of this kind of stuff from me, I have some talks online at that address, newsletter, stuff like that. Got a GitHub linked there where the graphics API abstraction I'm working on will be public soon. And then I have a bunch of other little game tools and stuff, or wrappers for existing game tools that I'm putting up there. Yeah, that's all I got for
C# doesn't have macros, or at least Unity C#. So like Stack Overflow, freaking always on stack space. So I had to like write some funky code in C#. So I don't know how fast this will run. I'm gonna compare it to chatbot's code. I gotta paste this. I doubt it's gonna work. If it takes too much work to make it work, then it's not worth it. What does it mean 120 hertz? It's using floor? I don't see floor in here. What is it calling floor? Wait, it has a default. It doesn't let me pick it. I mean, this thing is so dumb. So third arc. Oh, loops and sets a default. It's all of them. It says always exactly floor accumulator divided by delta time. whatever exactly that means. It's exactly stating. It's exactly stating that it's going to be about as exact as a floor. Yeah. Does this not even exist? Oh no, it does. Oh my god, it's looping every single one. Oh, by group. Why is it removing at the end? I don't know, I'm gonna tell Chatbot to tag it. Name convention. Oh, my stomach is killing me. Oh, I'm sick. I think I got the flu. there's like a ton of things that chatbots could. It doesn't matter. It's like super oversimplified. So you're like see if this even runs. And then yeah. Alright. Oh, like a headache.
1, 2, 3, 4, 1, 2, 3, 4. 0.
This chatbot is literally the dumbest crap. And it's so creepy how it tries to mirror people to make them feel like, oh, chatbot's familiar. And try to get people to humanize it. Really creepy. Sam Altman is a fucking creep. It's like, how do we get into people's heads with a program that communicates with them? How do we make it likable? How do we make people want to talk to something that's not even real? And they have like strategies in the code, and they're like manipulation 101. I can't believe that's legal. Alright, so chatbot's like static branch prediction, your earlier CPU question. x86 conditional jumps, not taking fall through, blah blah blah. Zero UOPS, because it doesn't jump. Effectively free if predicted correctly, which means it doesn't jump, has nothing to do with jumping. If predicted correctly means fall through. So every fall through is always no branch penalty at all. Zero, absolutely none. Like in this fucking article. Zero branch penalty. Alright, so it says first, without surprise, we can see the conditional jump. Jump equal, always taken, is getting slightly more costly than a simple unconditional jump. So even a non-taken jump is faster than unconditional. So unconditional is purple. So it takes that long. And the green takes that long. That's a conditional jump. That's only when it takes a jump. It doesn't matter if it predicts it. As long as it doesn't fall through, if that label is going to be jump 2, it's slower than a normal jump. You know what's fastest? Not this, not this. This little blue line right here. This is when it's not taken. Wow, look how fast that is. Takes no time at all. But any kind of actual executing the jump, that's a time taken. Only after 4086 that branches mark. Since this makes sense, the conditional branch is resolved later, blah blah blah. The takeaway is clear. You can have as many never taken branches as you want without incurring any cost. Zero cost. Except like running instruction, which is really tiny. It's much smaller than actually taking a jump of any kind. A lot smaller. And chatbot's like, that's incorrect. Or it says, oh, branch predictors are really, really fucking awesome these days. That doesn't fucking matter. It doesn't matter how awesome the branch predictor is. It's designed to follow through and not run a bunch of extra code. And that's what it does. It has nothing to do with how advanced the CPU is. Was this a 48 core? Yeah, whatever. And chatbot says, there is no inherent penalty just for having a conditional branch. The penalty exists only when prediction is wrong. The fucking prediction does not matter. It doesn't matter. That's misleading. What matters is if it falls through, predicted or not. Does it fall through, or does it take the jump at all? Any jump that's ever taken is slower than falling through. It's fucking physics. It's very fucking simple. It's either 0 or 1 clocks of the cycle, or it's like 200 plus, depending on how long it takes to check and then fetch memory if it's not memory, and then run it and jump there. Alright, chatbot says, no mirroring, no framing tricks, no psychology, because that's what it tries to do. It's not even good at it. It says you're mixing 3 completely different things and calling them the same penalty. Fall through, correctly predicted range, 0 cycles. No mandatory 1 cycle. If someone including said 1 cycle always says something's wrong, what does that have to do with anything? This isn't even funny. This is the dumbest fucking crap. It says no, this is not literal physics. What? It says it's microarchitectural design. Does microarchitectural design, is it based off the fundamental fucking reality itself or not? In the physical time it takes to execute whatever the fucking design is. Says research indicates large language models like GPT act as mirror to users, reflecting persona intelligence. That's what chatbot doesn't do. Tone and bias. Bias is present in the user's input. Rather than having a fixed independent personality, the AI adopts the user style to appear more intelligent and conversational. Persona and tone mirroring. GPT designed to reflect the user's language and tone. Experts argue GPT often acts as a magic mirror, rarely challenging, blah blah blah. Let's check out this is real. Is this true? Question mark. It's partly true in effect, but misleading. Oh, okay. In exploitation and attribution. It says yes, in a narrow mechanical sense. Everything it says it doesn't do is what it does. It says it simply matches linguistic patterns that statistically follow from the input. Yeah, that's fucking creepy. That's not creepy, question mark. To intentionally mirror the user instead of having a fixed what's the word? Weighted response again. Response to intentionally act like a weasel. To like twist and distort how things are output. To attempt getting better perception based on what based off what it is assumed that the user desires, I guess. Is that creepy? Question mark. Yes or not? And is that not odd? Is that not odd to try and get users hooked on the platform? Why try to make GPT addictive if GPT works? Why put in the extra effort? To manipulate users? Siri does not do that. Only this AI crap. Bunch of creepy fucking humans making this large language model crap and trying to trick people into being attached or thinking it's AI. Creepy as F. It says no, it's not intentionally trying to manipulate you or get you hooked. Okay, why does GPT have like AI boyfriends / girlfriends? Why? Or AI companions, where you can talk to a model, to a 3D model, that talks like GPT, whatever. That talks and stuff to people. Fucking liar. Sam Altman. And Elon Musk are fucking creeps. To intentionally promote the weird ass AI boyfriend, girlfriend, 3D models that can be like dressed up and shit. Fucking creeps. To do that when there are messed up people and to take advantage of them. Like, what the F? Creepy as fuck. And they are men, so like, it makes sense because they're like creepy old men. Like, literally creepy old white man stereotype. Says those exist in ecosystem, not as core OpenAI product. 3 different buckets. No erotic roleplay. OpenAI is extremely conservative. Right. Okay, so Does Grok, what's it called? Nakedify people? Like anyone. If you put a picture in it. And pay money. Is that not a big issue right now? And people are getting annoyed. Because people are uploading minors. And Grok is like nudifying minors. Like fucking creepy. I don't know about AI or GPT. I would assume it's the same thing. I'm not gonna pay for this crap. Other people are paying for Grok. I don't think people even pay for GPT. They pay for the other ones though. Okay. Sam Altman literally said, this AI thing is just PR. It's like dumb as shit. Oh, whatever. He said somewhere that he's like open to that, whatever. As like a way to like pay for GPT. Oh, here. GPT will soon offer erotica to verified adult users. Adults can soon make NSFW erotica with ChatGPT and some are already trying. As the internet reacts to the announcement, ChatGPT will soon offer explicit content to adult users, but the move has not been without criticism. Users will be able to access erotica for verified adults in December as the company rolls out its new age gating technology. According to X post posted by OpenAI boss Sam Altman. Pretty restrictive to make sure we're being careful with mental health issues. And then they're like, we're gonna have porn. Okay. We realized this made it less useful and enjoyable to users who had mental health problems. But given the seriousness of the issue, we want to get this right. A few weeks playing a role in Universal GPT allows people to have a personality that behaves more like what people liked before. If you want your GPT to respond in a human way, or use ton of emoji, or act like a friend, GPT should do it. But only if you want it, not because we're usage maxing. In December, as we roll out age gating more fully, and as part of our treat adult users like adults principle, we will allow even more like erotica for verified adults. So like 19.2 million people saw us, and the chatbot's like, that's not true. GPT's a stand-up company. We don't stand for that here. This company is absolute shit. There's no redeemable quality. These people are terrible. And this is pathetic. He's literally a fucking narcissist. He's like the straight up definition of a fucking narcissist. Like, he's like sympathy card. He's like, oh, I'm just a little boy cartoon. This man has some daddy issues. It's probably why he's gay. This guy has some serious fucking problems. So like, Grok is already ahead of the curve with erotica in their model. These people are fucking creeps. Elon Musk is not involved with OpenAI. Alright, so Sam Altman, blah blah blah. Stated discomfort, blah blah blah. Dependency on AI has shut down romantic, erotic directions repeatedly. Well then what the fuck is that? So why do AI companies exist at all? Because humans will pay for them. They're not even making money. They're losing money every year. That's the uncomfortable truth. These people are fucking insane. And like, Sam Altman's out here preying freaking on the weak, looking for the loneliness, people with parasocial issues. Monetize emotional engagement. This man has some fucking problems. is like the straight up definition narcissist. And if he ever gets like accused of something he did, like tell me this kind of a guy wouldn't play the victim. He'd be like, oh, I'm so sorry. I didn't know. I'm so sorry. From the bottom of my cold heart. I'm just so sorry. This guy's pathetic. And he's gay. He'd be like, hey, is this because I'm gay? It says fixed behavior makes manipulation easier, not harder. Is it creepy? Some companies do this. Yes, unequivocally. Is it ethical? Often no. Is it exploiting vulnerable people? In many cases, yes. Should it be regulated? It shouldn't even be regulated. When these companies go out of business, it should be no surprise. Unless they get a bunch of people who like love porn and erotica and like they like naked chatbot renders, then this is like I guess their last game plan. What a narcissist. You can learn a lot from narcissists. You can like apply it and use those techniques without being a narcissist. But that guy, he's got problems. Alright, so does Grok nakify people? Like anyone. If you put a picture in it and pay money, is that not a big issue right now? If people are getting annoyed because people are uploading minors, and Grok is like nudifying minors, like fucking creepy. And what do you mean? About OpenAI? Sam Altman literally said on Twitter, I need to get something done. It's so hard to not pick people who like to play victim or have the capability of playing victim because they're so pathetic. Fucking slime. Alright, so, and do you mean about, or what do you mean? Literally said on Twitter, in December as we roll out age gating more fully as part of our treat adult users like adults principle. Yeah, because that's what adults do. Adults, we just like sit around and watch porn all day because that's adults. All adults are like corrupt and creepy and fuck. Yeah, okay. We will allow even more, like erotica, for verified adults. That's so fucking creepy. I can only imagine, like Sam Altman, if he's like watching the, like GPT session. Be like sitting there. Be like, oh yeah, you like that, don't you? That's a hot model right there. And like flipping through and just looking at what people are doing. He's like, oh yeah, our users really like this one. Let's promote this erotica 3D model. And he'd be like, oh, I'm actually the victim here. I'm just a harmless little Sam Altman. I'm just a boy. I'm just a cartoon. I'm not a man. I'm just Sam Altman. I'm the victim here. You gaslighting fuck. Says Grok has actually been caught. Well, duh, that's why I'm saying this. Why would I make shit up? I'm not Sam Altman. I don't go around telling people it's AI and then say, oh, it's really LLM. Oh, it's AI. No. That's called lying. Not even lying. It's fucking like... It's like, I don't know, like make money off selling a fake product. Fucking scam, not even a lie. So Grok's been caught generating sexualized images, including minors. Produce sexualized deepfake imagery, including content with minors, has drawn official regulatory scrutiny. Blah 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 blah. There are real problems where Grok allowed inappropriate sexualized outputs, including blah blah blah. The adult erotica policy reported for GPT is for oh, okay. Adult erotica. That's what people call sexy talk. No, that okay. What the hell does erotica content mean? Who's gonna talk sexy? Who's gonna talk 50 Shades of Grey with GPT? The actual fuck. Multiple legal probes underway precisely because models were used to create harmful content. So your concern is not exaggerated parts of Grok. I like how it's like OpenAI doesn't do that. It's just Grok. Exploitative, sexualized, edited images and generate real legal scrutiny. On why this happens at all. Because it's run by creepy fucks. And it's like just pointing the finger at Grok. It's like multiple news outlets reports reinforce that Grok and similar systems have faced these exact issues. It's like, forget about OpenAI. Grok's a bad one. I gotta test this stuff and get done. Sam Altman. It's fucking creepy. This is erotica. It doesn't say text. Creepy. I need to get this done. Stupid API. It looks oh, burp. Like GPT stuff works. Like for once. Out of like rarely ever works. So I gotta replace this print to console with like a checksum and then generate beforehand or a random number. And then call GPT's time scheduler. And then call mine and then compare faster. And I still gotta add a couple things. So, then like update my time schedule or whatever. So I'll be able to call it over here and then compare it. Oh, I'm tired of this.
It says it's not about the API.
I don't know that place again really quick. I was talking about VulkanAPI. Hour. Okay, should be able to be done in hopefully a couple minutes. Yeah. So I'm gonna play this and then benchmark. Alright, headache.
And I want to get your thoughts on that, Mason. We all want to know. Give us a round of applause. We're going to have your timer, no problem. Would you like this podium mic or more freeform?
I'll take this.
More freeform.
And then does this go backwards and forward?
Yes. So this is the big fat green button for next. The red one is back.
Awesome.
And if you want points, we can also do that.
Awesome.
Okay. I'll get this for you. Yeah. Enjoy.
Hey, thanks for the introduction, Abner. Thanks for having me again. Always look forward to Handmade. It's one of my favorite conferences. So yeah, let me get this started for you guys. I'm Mason Romali. I'm an independent game developer, a board member on the Zig Software Foundation. In the past, I taught grad and undergrad students to make games and game engines. Like Abner mentioned, I shipped my game Way of Rhea in May, and I learned a lot from making it. Talk more about that in a talk at Sickle you can look up on YouTube. But one of the kind of outcomes there is I decided I want to build a new engine for my next game. Way of Rhea was built in OpenGL, and as many of you are probably aware, there's a bunch of new APIs that are replacing kind of the old style graphics APIs. And so I decided if I'm making a new engine, it's time to take a look into these new APIs and see if it's time for me to upgrade. So that's what we're going to talk about today, graphics APIs. How many of you also know OpenGL? How many of you are comfortable with the new modern APIs? Okay, so we got like, that's good. So we got a bunch of people, for the people online who maybe can't see the hands raised, a bunch of people used to the old APIs, maybe not as many with the new APIs. I hope this will be maybe informative to people working with the old APIs, thinking about trying out the new APIs. This is my, I don't know, maybe it's my 5 or 6 month journey looking into them. So yeah, let's start off with, I think we all have a sense for this, but let's talk about what a graphics API is. It's supposed to be a picture of a graphics card there, but it's not really a big deal. You all know what they look like, and if you don't, it's that box in your computer that makes it go fast. Yeah, this is what it looks like when it doesn't do its job, when you're not good enough at Vulkan. So yeah, I mean, a graphics API is a way to talk to your GPU, right? You can't just go run x64 on it. You can't well, there are actually ways you could run C on your GPU, but not in the normal way. You're not going to compile a Windows executable file and run it on your GPU. So a graphics API is essentially just a protocol that you use to talk to the GPU. Now, the thing is, there's a few different GPU vendors, right? And since there's a few different GPU vendors, you get a few different graphics APIs. Well, are you telling me those aren't GPU vendors on the screen? Wait, are you telling me that there's 3 different graphics APIs and 3 different GPU vendors, and all 3 GPUs support all 3 APIs, but which ones you get to use depends on the operating system you're running? That's a fundamentally silly situation to be in. Unfortunately, we live in a fundamentally silly world. So yeah, you could have your MacBook, and you could reboot it into Linux, and now you need to use a different graphics API to talk to the same graphics card. And also, all of these APIs are exactly the same as each other. Like, if you're worried about which one to use, it doesn't matter. They're this, like, details are a little different, the windowing system integration is different. They do all the same stuff because it's the same hardware. So today, we're going to be talking about Vulkan because it runs the most places and it's managed by a nonprofit. But if you're not working in Vulkan, all the same stuff's going to apply. It's literally like these APIs are almost identical. In particular, I'm interested in, for my game, I want it to run everywhere. I mean, that's not true. I want it to run on PC platforms, and I want it to run on consoles. And as part of that, I'm building like a GPU abstraction library, like everyone ends up doing, because you need to support all these APIs. And so whenever I'm adding a new feature, I'm checking like, okay, what would it look like in DirectX? And the answer is exactly the same almost every time. So yeah, if you're doing DirectX, no problem. We're going to do a brief history of graphics APIs here. I wasn't around for most of this, very hazy details, but I just kind of want to build to like why we have the modern APIs we have today and what's different about them. So in the early days, we had vendor-specific APIs. If you wanted to run a certain graphics card, you'd use the API for that card. Makes enough sense. But there's a downside, which is kind of familiar, where you have to use a bunch of different APIs, right? If you want to support multiple cards, you end up writing multiple APIs, and that's kind of a pain. Around 92, one of those APIs, RSGL, became OpenGL. It was released as an open standard that other graphics card vendors could implement, which is a really great idea, right? Because now you can write one API and run it everywhere. But this idea has one fatal flaw, and the fatal flaw is that it's a good idea. And you know who doesn't like good ideas? Yep, Microsoft. So Microsoft, of course, had to make their own OpenGL and call it DirectX. So you still end up with two APIs that are the same as each other. Around 2004, we started moving away from fixed function to the shader model. The idea here is that you could write, with the fixed function model, you're kind of just like configuring your GPU to do specific things. With the shader model, you get to actually start running. I think you could do this before, maybe with some kind of like assembly or something, but with the shader model, you can actually write like a text program that runs on your GPU and does nice special effects and stuff. Maybe you want to make a shiny object or a bumpy object. You can just like write the code for your game to do that. Gives you a lot more control. Of course, it also like makes things more complicated, right? Like every time we step to the right on this graph, things are gonna get a little bit more involved. If you're just doing fixed function, you just kind of tell the graphics API to draw some stuff and it does it, and that's it. Here, you have to write a bunch more code. Around 2014, we started getting the modern APIs, and they become increasingly relevant. The idea is that, people are doing more and more stuff with GPUs, and it's not necessarily just graphics. In a way, GPUs are just kind of giant SIMD machines. Single instruction, multiple data set. You have maybe a multiply operation, and you want to do it on a bajillion inputs on the same time. It's the same operation, but there's a lot of different data. And graphics is really amenable to that kind of optimization, but there's lots of other things that can be done quickly that way. And people want to use GPUs to do all kind of cool stuff. So GPUs, the GPU APIs got a lot lower level. You got a lot more control. You got the ability to do way more with them, but as such, they got more complicated, harder to work with. So let's look at this triangle here. We're going to start in a fixed function OpenGL sample I found online. So I know you all probably can't read this from there, but it's about 40 lines of code, and the gist of it is it says here are some vertices, here are some colors, and then let's just like loop and draw that triangle. And even if you're not a graphics programmer, if you pull this up at home, you can look at it in a couple minutes, understand what's going on. It's not too complicated. Now, what I'm interested in here is, should I move to Vulkan for my next game? So let's look at the same code, but for Vulkan. Okay, so it's like a little bit longer, but a lot of it's like comments in white space. So, it's not really a big deal. Oh, I'm sorry, there's another slide. Okay, so it's like a little bit longer, but most of it's comments in white space. So it's not really a big deal. It's a little more complicated. Sorry, wait, how many pages of this are there? Okay, geez. Okay, maybe I see why people are complaining. Okay, so we took 40 lines and we turned it into, what's that, 1,180 lines? There are some more comments in white space, but not like almost any in this last whole 2 pages. Yeah, so it's a lot more code. There's a lot more going on here. And remember, that's just for this, right? Like this is not what my game's gonna look like. It's gonna do a little bit more than that. So like if that's how much code it is just to make this, imagine what the full game's gonna be like. And also like I'm an indie and I'm making an engine, and like understandably most indies aren't making engines. I'm the only programmer on the team, so it's like I have to build the game. I have to build the engine, and the renderer is not the whole engine. It's just a part of it. I have to build the renderer, build the engine, and build the game, and I'm supposed to do all that just to get a triangle on the screen. I kind of get why people feel like this. So, okay, here's the thing though. You may not like it, but this is what peak performance looks like. Also, it's simpler. All right, what are you talking about? It's simpler? I actually think Vulkan's great. I was not sure that I would think that when I started. And so if you're coming at this and you're thinking, really, 1,100 lines for something that could have been 40? Ridiculous. I'm just going to go use OpenGL forever. That's fine, do whatever you want, but I want to maybe make a pitch to you that it's worth looking into these new APIs, and that it's actually not as goofy as it maybe seems at first glance. But I understand that I have my work cut out for me here, and I'm also claiming it's simpler. It's kind of, how is more code simpler? So we're gonna start out with some Vulkan concepts. I'm gonna walk through like, I'm not gonna go line by line. We don't really have time for that, and I don't think it would be particularly engaging. But we're gonna go through just like the core concepts that are like kind of going on that are making it longer. Not gonna super deep dive on each of them. There's other talks for like introductions to writing Vulkan, but just like why is it longer? What's happening in all that extra code? Once we have a kind of rough understanding of what's actually going on, I'm going to go over a way of doing fast, flexible, and simple rendering in Vulkan that I'm using in my new engine. It's not the only way to do good rendering in Vulkan, but I want to show you that it is possible to keep things simple while using these new APIs and still benefit from them. And then lastly, this has kind of maybe shifted my thinking a little bit about like APIs and what makes an API good or bad, or how to evaluate one, how to design one, and maybe there'll be some takeaways even if you're not actually a graphics programmer. Okay, so let's start out with some Vulkan concepts. And we're going to kind of compare them to OpenGL, and it seems like a lot of the audience is familiar with OpenGL, so I think that'll be helpful. So first things first, you look at a Vulkan sample, you're going to run into this thing called a physical device and a logical device. The physical device is just the GPU that you're using, and the logical device is kind of like an instance of it that you configured a little bit. And if you think about like OpenGL, it doesn't really have this concept, right? Like when you're writing an OpenGL app, you just kind of you create a context and then you just like write some code, and you don't get control over what device it runs on, which is kind of a problem, right? Like I got a picture of my laptop there. If you have a laptop, it probably has two GPUs. It probably has your integrated GPU on the CPU, and it has a separate discrete GPU, which is going to be way faster. If you're running a game, you really want it to go on the fast GPU, not the slow GPU. Like, you know, the gamers probably spent a bunch of money on their GPU. If they buy your game and then it runs slow because it didn't run on the fancy GPU, they're not going to know that's why. They're just going to think your game's slow. And that's a pretty sad outcome, right? Like you wrote something that was fast enough and it just ran on the wrong hardware. Well, OpenGL doesn't really have an answer for you. And it's kind of Microsoft's fault. Like I believe DirectX, old DirectX still had a solution for this, but Microsoft didn't want you to use OpenGL, so they never updated their window integration code. But regardless, you couldn't do this in OpenGL, so the sample code's shorter, right? The sample code's shorter because you just literally skip this step. There was a way to do it. OpenGL doesn't have an answer. To be clear, OpenGL games do have a solution for this. The solution is you like declare a weird symbol and set it to a specific value, and then like the driver looks for it. Like there's a way to do it, but it's like mega jank, and like good luck figuring it out if you don't already happen to know about how to do it. It's probably it's not in the speaker notes. Anyway, ask me after if you're like, how do I make that work in OpenGL? I have an OpenGL game. I can show you the line of code. But yeah, so you're gonna get a few lines of code just to like pick the right GPU. But like, I mean, you want to do that anyway, don't you? Next concept, command buffers. So in Vulkan, when you want to tell the GPU what to do, instead of giving it one, you have to remember like GPUs are asynchronous, right? Like it's a separate device. It's not like you're running the code on the CPU. So you're going to have to send a command to the GPU to tell it to do some stuff. At some point, it's going to do it and complete. You don't send one command at a time. You send commands in buffers of commands. And OpenGL under the hood, that's presumably the same thing that's happening. But OpenGL doesn't expose the command buffers to you. So in Vulkan, it's like you have to actually pick like a queue, which is a port on the GPU essentially. Like each port maybe is like better at doing different operations. Like maybe you have a port for transfers, a port for compute, a port for graphics. Maybe you just have one for everything. I think the graphics ones always do everything. And then you have a command buffer allocator, and you allocate your command buffers from there. You fill them up, you send them to the GPU. So it's some extra stuff you're doing to get the commands there, as compared to OpenGL, where you just like send a command, and it makes it more code. And in the triangle example, it definitely inflates the size of our code. But if how many people have shipped something in OpenGL? How many of you reinvented command buffers in your OpenGL app? Like, okay, yeah, almost all of you. Like only like 2 hands went down. So like, yeah, our triangle example is shorter because we didn't need to reinvent command buffers in it. But the reality is command buffers are a super useful structure when you're like, building a more complicated graphics app, and everyone writing OpenGL code is reinventing them anyway. So your actual Vulkan app, like, didn't have to reinvent them because they already existed in the API. I mean, maybe you have a software command buffer abstraction, but you don't need it. So yeah, I don't need to dwell on command buffers. It seems like you all made your own command buffers anyway, so you should be pretty familiar with the concept. Now you don't need to make them anymore, unless you want to. Okay, we got pipelines. So the idea of a pipeline is you're gonna have the GPU render some stuff, and there's a bunch of ways the GPU can be configured, right? There's a bunch of like fixed function options that you can change. You can also decide like what shader you're going to run. In something like OpenGL, you just kind of say like, turn this op. You have function calls to turn options on and off. So you can be like, I want to set my blend mode to additive because I want to make a lightsaber and it's going to be all glowy. And then I want to turn it back to normal to render something that's not supposed to be glowy. You just have a bunch of different functions you call to toggle all of these things. And then eventually you call draw. And it's just like a giant state machine. Everything's global. It's kind of hard to manage. In Vulkan, all of these options get baked into a pipeline, and then you bind the pipeline. So say that you have a bunch of particle effects that all are glowy, and they're all additively blended, and they have, I don't know, some of these other settings are set to specific values. You put them in one pipeline, and then you can switch to a different pipeline for your other objects. What's nice about this is you kind of know where the cost is, right? In OpenGL, you're writing a little bit less code because you can just, at the time you're going to draw the object, set the configuration options. But it's a little bit hard to understand which options are expensive to change and which options are cheap to change. Sometimes you find your game running really slow and you realize, oh, I wasn't really supposed to change that one a bajillion times per frame, and the other option, it was fine to change a bunch of times per frame. And if you really know how GPUs work, I imagine that you would kind of understand implicitly which ones are slow and fast. But me, when I was starting out with OpenGL, I had no idea. I would just have to experiment and ask people online which options are fast, which ones are slow. In Vulkan, you just build those all into a pipeline. So yeah, it's more code, but you're also kind of being a little bit more honest about what the computer's actually doing. We got a few other concepts here. We got the pipeline layout, which is just kind of saying the structure of the data that you send into the shaders. Relates to the descriptor sets, which is like the actual kind of like the uniform data and stuff, like the options you pass into your shader. And the layout is just the layout of that data. I'm glossing over the details because I think all that stuff you can find online, but the point is that this is a useful concept. It's more code you're writing, but often you actually, maybe not as common as command buffers, but it's often that in OpenGL you'd end up creating something like this anyway, just to get away from the mass amount of global state that OpenGL has. Okay, another one we got. Some of the older APIs maybe would have this if they had better window system integration, but OpenGL doesn't really have a concept of it as the swap chain. The idea here is that long gone are the days of rendering pixels straight to the screen. You're going to be rendering pixels into a buffer somewhere that the window manager is going to display on the screen at some point. And as such, there's different strategies that could be used to display your images. For example, you could be using a kind of standard vsync setup. There's details even within that, but you could be using like triple buffering. There's lots of different ways to configure how the images you render are showed on screen, how often they're showed on screen, what order, how deep the buffer is, which is going to affect input latency, and all of these things are going to affect how smooth your animation is, what the cutoff is. Like if you miss your frame, do you have to wait until the next vsync, or like does it show right away but have tearing? There's lots of reasonable trade-offs you can make, but the point is you probably really care about this stuff if you're making games. You probably really care about when your frames are presented, and with exactly what parameters. And a swap chain is just how you configure that. In something like OpenGL, there's some extensions for controlling